Hi, my name is Anna Job. I'm an engineering student at Cape Shore Community College, and this is a video presentation on how to use MATLab to solve for inductance in an RLC circuit using techniques introduced in the course EGR 214, Number Methods for Engineers. So the purpose of this manual is based on the fact that it's assuming that you have some kind of knowledge about RLC circuits and AC sources, as well as other physics 1 and 2 related competencies. So for this manual, I chose a few pages from a physics textbook, pages 856 and 57 of Physics for Scientists and Engineers with Modern Physics, just to help give a little bit more context to impedance and calculating impedance. So it'll help explain some of the relationships between impedance and other metrics. So things like current and voltage and frequency. But the most important equation that we will be focusing on will be for impedance, RZ. So the equation in question is Z is equal to the square root of R squared plus XL minus XC squared. So a little bit of term definition. Z is our impedance, and it is given in ohms. The R is our resistance of the circuit. It is also in ohms. Our XL and our XC. XL is inductive reactance, and XC is capacitive reactance. Both of those are also given in ohms. And so it's important to know what impedance is in order to figure out other details of the circuit, so you can figure out those parameters and understand those relationships and help ensure success for your project. So to help kind of understand calculating impedance on its own first, we'll look at a solved example from the text. So a series RLC circuit has a resistance of 425 ohms, an inductance of 1.25 henries, and a capacitance of 3.5 microfarads. It is connected to an AC source with a frequency of 60 hertz and a change in Vmax of 150 volts. So what we're asked to do is determine the inductive reactance, the capacitive reactance, and the impedance. So we're looking for our XL, XC, and our Z. So the way that this textbook explains finding XL and XC is by using angular frequency, W. For the sake of simplicity, I just kind of incorporated the formula for W, 2 pi f, into XL and XC and just replaced it naturally. So to find our inductive reactance, XL, we need our angular frequency times our L, our inductance. To do this, it's 2 pi f, so 2 times pi times our frequency times our inductance. When we do that, we get 471 ohms as our resultant answer. Moving on to the next, finding our capacitive reactance, our XC, it's 1 over W times C. Now we do the same thing with angular frequency and just plug and replace. So it will be 1 over 2 pi FC. Plugging in the variables that we know, we get 758 ohms. And finally, now we can move on to the impedance. To find our impedance, we need to know what our XL and XC are, because we're already given that resistance, or R. So when we plug all the variables into the equation, we plug in 425 for our R, 471 for XL, and 758 for XC. We get 513 ohms, and that would be our answer for the impedance. So this process in itself is fairly simplistic based on all the things you would consider doing in physics 1 and 2, but still having to do the work, having to write it out, doing it analytically takes time. And time is very precious for an engineer. So to help kind of reduce that down, for this project, I made a code to help make that process a little simpler, to help ensure accuracy and efficiency. So if we look at the tutorial problem for number 1, we have a similar situation, except this time our resistance is at 40 ohms. Our inductance is 3.00 millihenries, and our frequency is 60, and our capacitor is at 5 microfarads. Another thing to note that is important is make sure that you convert your units back to its base unit. So for 5 microfarads, you want to make sure you convert that back to farads. So looking at the analytical solution, it's the same process. You solve for XL and XC, and then you plug everything you know into Z and get 531 ohms. So to make this simpler, I formed a function for in MATLab. So this function is solving for impedance using your resistance, frequency, capacitance, and inductance. Just for notes, that is also re-explained with the variable dictionary to help you understand a little bit more about what those variables are and what the values should look like. Moving on to the code itself, we solve for XL, or 2 pi FL. We substituted that angular frequency and just replaced it with 2 pi F. XC is 1 over 2 pi FC. And then we take both of those variables, those new components that we solved for, and plug it into Z, which is our square root of R squared plus XL minus XC squared. To help make sure that the answer doesn't get lost in all the chaos of MATLAB with the way the workspace works sometimes, I added a command to display the value of impedance is, and it will give you the resulting answer. This is just to help make things a little bit more clear and concise to understand. So to invoke this command with the same numbers from our tutorial, you just plug in 40 for your R, 60, and then remember how we need to convert those back to those base units, which is why we have so many zeros in for our 5 and 3. So that will give you a value of impedance of 531 ohms, which is similar to what we got originally in the analytical solution. So as you can see, this process is just as exact as needed for this situation, and it will give you the right answer every time, as long as you know that resistance and that frequency, the capacitance, and the inductance. So same thing with problem 2, different numbers, same setup. You plug in your known values and you get similar inductances or impedances. So going through each of the problems will give you the same result as you go through. And so that brings us to our concluding statement. So this manual is important because it will help ensure your design success by explaining the concept of RLC circuits in a simplistic way, and improving accuracy by incorporating the use of MATLAB to find a numerical solution rather than taking the time to have to do it analytically. By being able to accurately and quickly determine these parameters of a circuit, one could potentially avoid many future issues that could range from a minor setback to something a little bit more serious. By creating this manual, I hope that the concept of what impedance is and its relationship to other components in the circuit can be more easily understood and easily applied to real-life situations. All right, so that's all I have for you all today. Thank you so much for your time, and I hope you have a wonderful rest of your day.